Hi, a very good morning to all. This is Katya, your webinar coordinator. Very glad to welcome you all for the webinar on digital twin. Let me introduce our guest speaker, Mr. Eric from Burr Oak Tool. He's a control and software engineering manager. Eric has more than 29 plus years of experience in control, focusing on new product development. He started his career as a software engineer, writing software for multi access server control machines. In 2004, he helped develop the first Burr Oak Tool machine to use Siemens controllers. He is leading the company's digitalization initiatives, including Industry 4.0 and the digital twin. And our other speaker, Mr. Naresh, Director of MN Engineering Solution. Naresh has extensive experience in research and development, new product development, process and product optimization, production automation in the truck and trial, life science, and industrial machinery. He's also taking care of the digital transformation. Regarding Q&A, if you have any questions regarding the webinar, please send the questions in chat window and we'll collect the questions and we'll answer one by one during the Q&A session. Handing over to our speaker, Mr. Naresh.
Thank you. Thank you very much, Katia. Very good morning, good afternoon, ladies and gentlemen. Thanks for joining the webinar session today. It's been interesting. We've been talking about taking this webinar for a long time because everyone was talking about digital twin, and we have done quite a few deployment in US and Europe with our customers regarding the digital twin. So today we're going to talk more on the introduction on digital twin. What does actually digital twin mean? I mean, most of us here might know what is digital twin is, but I'm just going to touch base on it before we get into the actual technical session. And also, I'm going to touch base on digitalization. What is digitalization and how it has been transforming the world today. And I have my good friend Eric here, so he's going to share his view on why Burr Oak Tool actually chose digital twin in their commissioning process. That was actually during COVID time when they had a lot of restrictions to people to actually go into the workplace and do the actual commissioning process. So we helped them out, and our team in India completely worked it on the commissioning process from the offshore. So that's pretty interesting. We have a demo on it. So I think that would be very informative for you. So after that, we will talk more on the do's and don'ts. What are the issues we face so far by doing digital twin, and that will give you a clear idea what you shouldn't do before you actually start with the digital twin project. And definitely the final thing is the cost benefits and the challenges we face. It's back to Eric, how they actually overcome digital twin technology, because since it's new, many people doesn't have the awareness to how to actually do that. And this is a session we're going to touch base on every single few things before we actually go into our upcoming sessions, where we will talk more detail on the deployments and real-time monitoring and much more in the technology. So what is digital twin? So digital twin is nothing but, before I go to digital twin, I'll talk about digitalization. Digitalization is a process of converting your manual, mechanical, everyday process to the digital world. It's just whatever it can be. I mean, it can be a sales order that's passed to the engineering department, and once the engineering department figures out how to do it, it's just passed into the BOM department, right? I mean, every single let me put it in a different way. So every single system, let's say you have a PLM, you have ERP system, you have warehouse management system, you connect everything together with a thread. We call it as a digital thread. A digital thread is an invisible pipeline that connects into departments so that the information is transferred. So why digitalization? You might be very happy doing that in manual process every day, but digitalization has its own value. I mean, you're gonna save cost in long run. It will be more. It doesn't depend on human. It's once the process is set, it goes as it is, and also you get feedback. So when you get feedback, there is always a chance to improvise your process. So that is why people are going to digitalization now. So let's take a deeper dive now. What is digital twin technology? So digital twin is nothing but having a physical copy or a virtual copy of your physical machine. Say I have a remote or have a mouse here. So I'm just going to take a digital copy of this. When I say digital copy, it's just not CAD model. It's just not a simulation model. It's more with behavior in it. It will act and react the same way you do it in the real world. So you can actually bring in your real world environment and simulate your product based on the real world aspects so that you know how your product reacts. So that is digital twin that we're going to talk about. There are many values to it, but as we go, I'll start giving more inputs on it. So I'm just gonna, before we go next, I mean, I just want to share some information that's conducted by Alter. So Alter is a big research company. So they conducted a survey on what these companies are done. So they picked 2007 companies of different industries, different verticals, might be pharma, automotive, or just machine manufacturer, whatever it is, they brought them together and they asked, have your company done any digital twin process before? I mean, to be honest, there are about 69% of the organization they talked with already did something on digital twin. So where they are, when they started doing it, that's the chart on the right side. You can see most of the development when they started talking about it. Initially, when they started doing it, it was about 3 to 5 years ago, and most of the development happened just 2 to 3 years back, and recent developments are the extreme spike. I mean, you can see in 7 to 11 months ago when they started talking and implementing more on the digital twin. So it's getting popular. And if you see the CAGR, it's quite really a lot when they are running at 33% CAGR every day, every year. And we are expecting it's going to be more than some billion, about $2 to $5 billion market in the next few years. So this slide talks about what are the major advantage of implementing digital twin in your company. So the first and foremost, topmost advantage is the real-time monitoring and control. So when you have your machine deployed in your customer place, most of the service calls, if you see today, are stupid. It gets fixed if you just turn on or restart your machine or something like that. But you have to send your service engineer to your customer place all the way and try to fix it. But if you monitor your machine from somewhere, just sitting at your desk and how it is performing, you can actually do the diagnostics also. So you save ton of money and your customers will be free of any downtime. I mean, if you can predict it much earlier. So that's number one. Number two is definitely efficiency and safety. So today, if you see the efficiency, most of the companies OEE of the production plant, it's about 35 to 45%, and everyone is dreaming to achieve 85. You cannot do it by manual process. You definitely have to get into a digitization process, do multiple iterations, try to see where you actually boost up your OEE so that it will definitely benefit you on the long run. So that's the second advantage of doing digital twin. And the third one is obviously cost saving. So that is what we're going to talk more, how Burr Oak Tool save time and also cost by implementing the virtual commissioning process in digital twin so that it helps them out on getting their product really fast to the market and also help them in achieving the desired result on monitoring and also on the future prospects. So I'll hand it off to Eric to just show some light on why they actually chose digital twin. Over to you, Eric.
All right. Thank you, Naresh. So, for those of you who are software engineers, how many times do you have enough time on your projects to do all the testing, debugging, commissioning of your software on your machine? As I look back at what I've been doing, I can't think of a single project where the machine was finished in design, the parts were all manufactured, the machine assembly was done on time, and or even early, so that I could have all the time for testing the software that I was promised. So No, it's usually all that time in the project schedule is usually used by everybody else upstream. And then for those of you who, are usually waiting and don't do software engineering, how often are you waiting on the software engineer to finish and wondering what's taking so long? So to avoid that problem, Burr Oak Tool was looking at a machine that was new to us, had lots of innovation, and it's the first time we designed and built it, and we also had a customer who was waiting for it. And to tighten up the project schedule, we decided to utilize a digital twin to do virtual commissioning of the machine, hoping above everything is to save some time so we could get the machine out and delivered to our customer. And obviously, we're hoping to, as Narisha talked about, do a lot of our software testing during the machine assembling and machining of parts phase of the project. And one of the things we did, we're looking at identifying and eliminating design errors. For us, a project engineer, a mechanical engineer, and a software engineer spend time together defining the functions of the machine. Well, with the digital twin, now we can look at what that sequence of operations is on the virtual machine instead of waiting until the physical machine is built. And that'll save some time because all the changes can be done to the software and the sequencing early on. One of the unexpected benefits that we had is by running the simulation or running the digital twin, we were able to identify a few parts collisions. And so the mechanical engineer saw that. He was able to run the simulation with the software sequencing and modify the design, the physical design of the parts. We had an actual additional benefit is that those parts had not yet been machined. So there's no scrap involved in the parts that he had to redesign. Oftentimes, I think all of us are aware that some of those collisions aren't discovered until the physical machine is built, and then everything stops while you have parts remade. Working with MNES with the digital twin showed a lot of collaboration between Burr Oak Tool and MNES engineering. That also helped us with our internal collaboration and making sure that we could see how everything worked in the software world. So what our PLC auto cycles look like. I guess one of the things we also talked about is reducing risk and potential damage to during the commissioning of the physical systems. I think most companies understand that you use your 3D CAD model. You can show it to those technicians who are assembling your machine and building the parts, helps them understand what it's going to look like and make sure the assembly goes together correctly. But now, when we showed them how the machine was actually going to operate in automatic cycle, they had a better understanding of what they were building and how it would operate, and actually added a lot of valuable insights and suggestions to the way the machine would operate. So we got a lot of benefit from that. Also, by exercising the auto cycle, the PLC software on the machine, we were able to be very confident. And that kind of leads into also non-destructive testing of the machine. So by the time we had revised and reiterated or gone through an iterative process, both internally with our project engineer and mechanical engineer, and then also with M engineering, we were really confident that the sequence of events on the machine from the PLC would be accurate and correct and not cause any machine damage. And we realized that, and we were very happy about that. The cost benefit, probably going into the digital twin wasn't the primary goal. Really, we were looking for a time savings. But I think we all understand that by saving times, we're saving cost. We reduced the debugging time and the testing time on the physical machine. And that was a nice way to save money, as was being able to save money on the parts that we were building and making sure that everything was good. Nourish?
Thank you, sir. Thank you very much. Yeah, you put it in a very good way, Eric. Yeah, when you save time, you save money, and also doing repetitive work. I mean, you don't want to do multiple iteration of the same work again and again, and it's gonna take a lot of cost to it. Fine. So now we are going into the deep technical aspect of how we did the digital twin. So the digital twin, just assume a digital twin is a human body, right? So in order to take a human body, you need the brain functions, you need the motor skills, you need the body actually, the solid form to actually perform. So it's the same way. I mean, I just want to put this in the analogy. How do we call a digital twin a virtual copy of your system or your machine in a virtual world? So when we talked about it, Burr Oak Tool gave us the 3D model of the machine. So we got the 3D model, but the 3D model is just a dead body. Doesn't have physics to it, doesn't have motor skills, doesn't have any dynamics to it. So in order to do that, we need to import the model as parts and then reassemble it and start giving the physics attributes to it. Say you need to tell the machine like, hey, this is a servo, this is a cylinder, this is the maximum reach of the cylinder it has to retract, and these are the sensors to it. So you say this is a temperature sensor, vibration sensor. So all the definition of the physical attributes, you got to define it, and at the end you get a dynamic model. Now, a dynamic model, when I say it, it's just a zombie. So from 3D model creation, you bring it to a dynamic model by adding physical attributes to it. And now the dynamic model is actually a zombie. It can move, it can work, it can view, but it cannot think. So the brain is actually the PLC program behind it. So the PLC program is what when Burr Oak Tool gave us some similar programs, we got to upgrade to it, and then we got the program, but the program cannot directly fit into the machine. So it has to have a PLC that can actually process the program and send out the information to the model so the model can work as instructed by the PLC. So that is where the control program developments are. We connect the networks, the logics, map it with a virtual PLC. So in this machine, we use Siemens S7-1200 PLC. So we got a digital version, or when we use a software called PLC Sim Advanced, where you can actually have a virtual PLC. So we connect the program from TR portal to the PLC, and the PLC can actually give the instruction to our dynamic model. So by connecting to that, now you have a zombie and the brain both put together, you have a digital twin. So digital twin of your machine, it can perform the same way as it is performing in your physical world. So what are the end results we got from it? So when we start simulating the program, I'll show you the demo how we did it. So when we start doing that, the first thing was collision detection. So when I say collision detection, so they gave us a 3D model right after making the drawings or the prints for the manufacturing. So we started doing the software development and the commissioning process when they are actually manufacturing and assembling the machine together. So when we are able to find any collision detection, as Eric said, we will send to the engineers in Burr Oak Tool, and they will immediately create an engineering change order and fix it right away. So this is like happens really on the fly. So it helps them to actually reduce the time or the replication process at the end. When you figure this out at the end, when you put the machine together, you got to scrap the part or do the modification and then make it fix. Some areas we felt like, no, it cannot happen when the machine is designed as it's intended, but we got to tweak up the software program. So all these things, we were able to do it when they are actually putting the machine together. So that's the first agenda or the result that we got is the collision detection. The second is validation, program validation. That's our main concept. So we got to commission the program so that when they have the actual machine in place, we can just plug the program in it, and it's already 95% commission. So when I say 95% commission, you got to do minor tweak ups on the other manufacturing process. So obviously there's going to be stack ups and tolerance to it. So you just do some small tweak ups, and then the machine is ready for the final FAT. So these are the benefits. We define the goals. This is what we're going to achieve from doing this virtual commissioning, and that's how we did it. So let me run a quick demo on it, how we did the commissioning process, and then we will go back to our presentation slide. So first, when we start getting the model, the 3D model, so what we do is, as I said, we start defining the servo controls, the actuator controls, the cylinder controls, everything in it, and we want to do a manual testing. So when I say integration sequence test, you reassemble the machine together, and then you start defining the attributes, the physical attributes to it, and then we check it. So this doesn't involve any PLC program in the backside. We manually check it to make sure it's doing as it is intended to do. So this is the machine. We took out the guardings and all the safety light curtains and everything from it because, yeah, it's a virtual machine, so we don't have to worry about the safety in here. But as you can see, this is a manual check process where we just want to move the servos, move the actuator, and see how it works. Now, the second step is where the PLC comes in. So now we integrate the machine with the PLC program. So that's where the functional test of the cylinder. So when you define the cylinder has to work in multiple ways. So when it's turned on, it has to move up, and when it's turned off, it has to move back, right? So that's how we defined it. So when we start doing that, we want to check if the cylinder is performing as it's programmed. So you can see here, we started giving manual checks. We turned on, turned off the cylinder and seeing if it is working or not. So once it's done, yep, the cylinders are checked. Let's move to the servos now. Servos are kind of tricky because you got to give the RPM, the rotation per minute, and also the pitch or the moving distance, the pitch has to be calculated. So every single data are taken from the real world. So when we have, let's say you have a Festo server, a Festo cylinder, or any actuator for that, when you just take the data from it, from the actual spec sheet, and put that in the machine so that it performs as the actual machine in there. So you can see the distance it's moved and also the rotations on the servos. So now, after doing all the individual tests, we make sure, yes, our digital twin is working as it is, as we plan to intend to do it. So now let's connect all of them together. Then you connect the cylinders, servos, everything together, and do another manual test before we go for the actual physical test. So when you see here, we took out certain script from the program where the cylinder is connected to it and the servo is connected to it, and then we run the simulation for it. So this is again a manual check test. So you can see here, let me replay it. So when you turn it on and off, it can actually move and see if it is working. So the next step is actually identifying the collision. So when you do all these manual checks, you will be able to see some collisions, or I mean, if you know a machine at the first phase, like as it's planned, right? When there's always human errors are there, and having like 1,000 parts on a machine, you might end up making some mistakes on the assembly or some issues. So this is the very crucial step where you can actually identify the collisions. So when you identify the collision, you'll be able to figure out what are the issues. Is that a manufacturing problem, or it's a mechanical design problem, or it can be fixed through the control software. So here you can clearly see there is a collision detected when you try to move it, and it immediately shows an error like, yep, there's a collision here, fix it right away. So we send that to our customer, and they immediately create an ECO for it to make the necessary changes. So once all the manual checks are done, the collision, now the machine or the digital twin is collision free, we will move to the final step. That's where we call it as auto cycle test. Auto cycle is nothing but a recipe cycle test. When I call it recipe, with all our machines today, if you see, there's an HMI, and it's like a microwave. You just select with the popcorn on it, and then throw your product in there and close the door. And after 3 minutes, you will get your popcorn out. So, in similar way, all these machines are programmed in recipe mode. So, recipe modes are like full a sequence of program in it. So, all you got to do is your operator will load the raw materials or the product assembled parts and then select the particular recipe. The machine has to do all the sequence of operation completely and close the loop, and then when it's done, you get the final product out. So this is the most tedious process, and this is what we actually want to do, a full cycle test and figure out if our programs are right. So that is what we are doing on the virtual commissioning side. So if you can see here, so now we integrated everything. This is the HMI screen. So when you start loading the program and press start, you can actually see the steps going in there. So you can see the cylinder gets clamped, and then the tailstock or the bottom part gets clamped, and then the header moves. So all the sequence of step gets the feedback, and the next step begins. So that's how the cycle is done. So this is the complete HMI, and you can see on parallel, you can see the programs that's getting executed. And if there is any error, it will show you where the error is. So every single step is monitored when we are running the full cycle program, so that we know where the problem is and we can tweak up the commissioning side or the program to make it work better. So once that is done, we get the program and we send it back to our team and ask them to do a final check. So the final check will actually be there on the facility. And when I say it's 95%, 95% is completely done. So you got to do some fixing on the process when the manufacturing stack ups later on. All right, so now we saw the demo, but most of the people have this question. So what is right and wrong in digital twin? We cannot say these are things are right and these are things are wrong, but based on our experience on deploying multiple digital twins now, these are some of the do's that we always have as a checklist. We make sure it's done. So first thing first, it's you gotta have the objective. So when you have the digital twin, we had a clear objective on this machine. Yes, we got to do the virtual commissioning, and these are the outputs for it. So if you don't have the definition on your digital twin, why you're going to do it, then you won't even reach there. I mean, it's always like looping around back and forth, and you always lose your track. So always please plan your objectives when you implement a digital twin. Use accurate detail models. Yes, when I say you gotta add the inputs of all the tech sheets, when tech data sheets, when you define even a sensor, you gotta define all the information for it. So if you don't define and you just go by assumptions instead of the real numbers, then your values or the commissioning process is gonna fail. So you need to have the model in there, the digital twin in there, as accurate as possible, including all the purchase components, validating against the real data. So you gotta consider the real world data too. So when you have the environment around you, as I said, we took out all the fail-safe controls, all the fail-safe PLC interface blocks. We got rid of all the guardings and stuff because we know it is not required at this point of time. We actually checked a full cycle machine later on with all the guards and stuff, so that it's just for fun. But here you gotta see what is actually required and what are the details you are trying to simulate as real as possible as the real world data. So make sure you're cleaning up all your boundary conditions and define your data sets based out of it. Test various scenarios. Yes, what if is the basic thing that you can do on the digital twin. So when you do it on your actual machine, it's going to take time. And when you do an iteration on your machine with different controls and different, when you try to play around with different scenarios, it usually takes time and you won't get the result as possible. But here you have a virtual machine, so you can play around with whatever you want to, and you can stick around with your the original design, or you can just try to simulate and see if it performs better in a different way, and then you can just implement it. So that's a pretty cool thing about digital twin. You can play around with a lot of stuff. Collaborate with stakeholders. Yes, that's the biggest thing we achieved with Burr Oak Tool. And we actually gathered all the mechanical and the controls people together, because it's always universal. And the mechanical engineers design the machine, the controls, when they know the philosophy of the machine, the controls engineer have the other way of feedback to it. So you bring in, you collaborate everyone. So including us, as Eric said before, M&ES was the offshore team supporting them on the virtual commissioning, but they got to feed us all the information so that we can actually make the digital twin better. So always collaborate with your people. Don't go by assumptions. Don'ts. What are you shouldn't do when you do digital twin? Don't rely on virtual commissioning completely. Yes, there's always a 5% chance of doing or going something wrong because of a lot of external activities. I mean, you have different environment situations. So you always depend on the real world, but the virtual commissioning is a tool that helps you to make your actual commissioning or the FAT in a much faster phase. When it can complete the loop in a much faster scenario, rather waiting and doing it for 2 months, you do it in 2 days. That's the main goal of virtual commissioning, not to completely eliminate it. So keep that in mind. Real world constraints, as I said, make sure the constraints are always limited in the digital world. When we are still not there completely yet, but in the future, you can simulate a lot of things. But today, with the constraints we have, we can do certain limitations. We got to consider that in our digital twin phases and react based on it. So integration with the other system. So here, this was a single machine, but if you have a downstream and upstream process, then always consider that when you have the input to come in and the output to go out. So always make sure your upstream and downstream process are interconnected. So that is something you shouldn't miss out. Data accuracy and integrity. So always have the accurate data, as I said, but you got to do and update data. When you have a PLM system, you after doing the digital twin here, someone would have done changes on your machine already. If you don't replicate that in the digital twin and you don't do the iteration for it, then the program or whatever you have today, it's outdated already. So make sure whenever you do it, keep in mind your digital twin is always updated when there is a change on the actual machine. But in PLM today, everything is interconnected. Even our digital twin is closely attached to the CAD-based PDM server. So don't have to worry about it. It actually updates it, but make sure it's updated. That's what another check we should do it. So skipping documentation and knowledge transfer. Yes, that's the biggest problem when we started implementing digital twin. We have multiple teams. We have mechanical team, embedded team, and controls team working together, the electrical electronics engineers, and it's multiple team collaborating together, and we will lose the track if we do some changes on it. So every single milestones when we achieve, we make sure it's documented so that we can go back in the track and see if there is any problem to it. We can actually go back and fix it. So always make documentation. Do not skip it. It is gonna help you out even when you go to the next phase. So when you decided to go with real-time monitoring and you want to upscale your digital twin, you definitely need the backup on the current documentation so that it will help you to go much faster. Please do not skip that process. So I'm just going to give you some examples on the softwares we use for virtual commissioning actually. So when I say we want to create the zombie, we created the zombie with Siemens NX MCD. So that's a software we use, Mechatronic Concept Designer. So basically it can actually identify the servos and the cylinders or whatever the sensors that's in place. It actually gives more kind of kinematics to it. But if you want to add more behavior to it, then you should also consider Simit. It's another process tool where you can actually add more behavior to a machine. So, but for this project, we didn't consider that. We just stick out with the MCD. So, because we just want to do the full commissioning on the mechanisms, not on the complete behavior side. So for the brain part of the machine, we used TIA Portal because it's Siemens 1200 PLC. So we use TIA Portal. But if you use Allen Bradley, yeah, there's Studio 500, there's FANUC, and whatever the PLC you want to use it, there is no restriction on the PLC. So you can definitely build digital twin on multiple PLCs. And then virtual PLC, as I said before, we use PLC Sim Advanced. That's where we can actually create the virtual PLC controllers for it. And even for Allen Bradley, you have RS Logic simulators. So you can create a digital twin of your PLC and then plug it to your digital twin and see how it works. So these are some of the softwares we use for virtual commissioning. There's also advanced simulation softwares. Say certain area for real world scenarios, we use SimCenter and ANSYS Solver sometimes because we want to get that result and feed it back to our digital twin so that we can perform the real time or the real world scenario to it. And if you are, say, for example, you are doing it a factory twin. A factory twin is a copy of your entire factory or your shop floor. So for that, we use Technomatics, Flexim, or Technomatics is basically from Siemens, Flexim, or Arena from Rockwell Automation. So these are some of the softwares available today for your digital world to bring your shop floor to the digital world. And there's a lot of other softwares that's also in place, but these are just some examples that we give it out for the webinar today. But as we go, as we progress, there's a lot of other softwares we use for real-time monitoring and even for predictive analytics that would be the topic of discussion for upcoming seminars. All right, so with this, I will hand it off to Eric to talk more on the benefits, what they got out of doing this virtual commissioning. Over to you, Eric.
Okay, so yes, the benefits. And one of the ones that everybody wants to know about is how do you reduce the lead time on a project? That's what Burr Oak Tool wanted to know. And what we did is we used the digital twin as frequently and as often as possible and used it to validate our software functions. And as you saw in the video demonstration, we could test not only the PLC cycles, but also the HMI. So as you interface with the HMI, you could press the buttons, you could see the feedback, you could look at the ladder and see what steps we're going through. It truly was like using the real physical machine. The other portion of where you're going to save in your lead time and reduce that is to make sure that you're using that digital twin as early in the design process as possible. We want to make sure you're using it during the design cycle when your machine or your project is still on paper. You want to use it during the manufacturing process. So at Burr Oak Tool, we build our own, or we machine our own parts. And so we want to do it during that portion too. And then of course, we want to save time by testing all that software during the assembly process when our technicians are building the machines for us. And then what are the benefits to, well, finding mistakes and errors? With Burr Oak Tool, the project engineer is the one who conceptualizes the whole machine. How is it going to look? How are we going to build it? How are we going to size it? And then also, what is the sequence of events? How is our customer going to use that machine and what's the process? And so he'll work very closely with the controls and software engineer to explain to him what his vision is, and then it's up to the software engineer to interpret that and implement it. So oftentimes it's not until the machine's running that project engineer can see if the software engineer understood him, and if not, then changes need to be made. Well, now what we saw was, hey, everybody in engineering could review the operation of those sequences, the way the PLC controlled the machine, the way the operator interacted with the HMI, and make sure everybody understood the same thing. And if changes were required, well, it was done well before the machine was built. And then earlier today, I talked a little bit about how we were able to detect part collisions. And so if you take advantage of using the digital twin early while you're still doing the design process, that gives you an opportunity to redesign parts that aren't quite right. And Narisha talked a little bit about that too, is how we could send those models back and forth with them and test them thoroughly in a virtual environment before we had to wait for parts to be machined. And that saved us money, of course, because we didn't have to remake some parts, but it also saved us time because you don't have to wait for that manufacturing process to occur, which is also part of shortening the design cycle. And I guess I would reiterate that use that digital twin often and use it for everything. We went into this project looking at how can we reduce the software testing time and shorten that lead time. But being able to test the mechanism and also the HMI, how that operator interface works, was an excellent way of shortening that the lead time that we had on our machines. And of course, rigorously testing the PLC sequences. So by the time we were done testing code and going back and forth at Burr Oak Tool and also with MN Engineering, we were really confident that that machine was going to operate the way we wanted it to. And we didn't really worry about the machine going through any bad motion and causing damage to a machine, which would have extended the development time on that machine. And then we can also talk about, hey, how do we use this to train our equipment operators and supervisors? And I mentioned previously that, we could use that with our assembly technicians to show them not only what the machine would look like, but also how does this machine operate, and that they could participate in that. Another thing that we have had is we've had some of our customers approach us and say, hey, we don't like to do our training on the machine because it takes the machine out of operation, making parts and making money for us. So can you send us just the HMI portion and make a training device? And so we've done things like that. What works even better then is if we take the digital twin, apply it to that training device, and then let the operator, our customers' operators, practice using the machine and learn how to use the machine. And not only are they learning the layout of the HMI, but they also see the consequences of the choices they make when they operate the machine. They see how the machine runs. They see what happens if they don't do the right sequence, and potentially damage that would occur, all safely within a virtual environment where it doesn't need to have replacement parts. So there's some challenges that we ran into, and the biggest challenge for Burr Oak Tool was the lack of personnel to build and use that digital twin. So our mechanical work is done in SolidWorks, but we needed it to be converted or ported over into MCD. And MN Engineering took care of all those problems for us, and we worked hand in hand with them, sending them our SolidWorks models so they can make the conversion, run the testing for us. We would write our software, our PLC software, send it to MN Engineering. They would run it through the model and report back to us very regularly. So we were meeting regularly, and we were getting reports back all of the time, which helped us move quickly on this. Burr Oak Tool had used an MCD in the past on previous projects, but we didn't have as much experience with integrating servo motion. And this is where we could turn to M&N's engineering and let them handle those functions for us. And so then we could get the full motion operation of the machine, again, like you saw in the video demonstration that Narish showed you. Now, another challenge that we had was because of the way the digital twin was built, we didn't enter in a lot of the material properties, so friction components of parts wasn't in there. So when it came time to actually starting the servo portion of the physical machine, we still needed to enter the drive parameters on the physical machine and then do the tuning, because the model wasn't developed enough to handle all those. But that didn't take as much time as it would have to commission everything else on the machine. So that was a challenge, but not a bad problem. something that we're used to doing all the time. Another challenge that we had is Naresh had spoken a little bit about how you can now connect your virtual model and have data from the physical model to provide feedback to your virtual machine and provide additional insights into the way the machine operates. We had a customer waiting for the machine, so we did not have time to do that part. So that was a challenge, but it would that's definitely an action on a future action that we want on our digitalization path, so that we can utilize those benefits also. As we think about that, we look at, okay, well, what future benefits do we have from this, and are we anticipating? So this machine is still fairly new with our customer, but often our customers are asking us to make refurbishments or retrofits and maybe modifications to the program, and there can be some challenges in that because we don't have machines that we can make those tests on at our assembly facility. So we look at this now and we think, wow, we can do the same thing that we did at the build for any modifications to a machine. We can create the parts and then we can run them and test them on the digital twin. We can make the software changes associated with those retrofits or those modifications and test them on the virtual machine. And then everybody can have a high degree of confidence that the changes we made will be functional. And so this means that we can do all the testing, or at least 90% of the testing, in a virtual environment before we take the time and the expenses to send technicians into the field to work on our machine at a customer site. So we look forward to that. We talked to another future benefit that we see is that our machines are very large, and so taking those to a trade show or visiting a customer with a machine isn't very practical. So what happens though if I can take on a computer the digital twin and do a virtual demonstration of the machine? Let the customer at a trade show or maybe at his office use an HMI to control the digital twin and kind of have a feel for what they're getting into. I think that would be a very big benefit that we're looking into. And then we're anxious for the physics model to improve and mature. We expect a lot in video games. Why can't we have it here? So already gravity is a portion of, or is modeled in this digital twin. But what about part deformation, frictional components? Those would be a nice thing to have involved in a digital twin also. Our business is to cut and size tubing, and so it'd be nice to see how our tooling works inside that tubing. And then I think the biggest thing on everyone's digital journey is to make sure that the full digital thread is used. And when we start extrapolating that data, then we start getting into the ability to do predictive maintenance. And I think in the future, this is something that everyone will demand and need to use, and that OEMs like Burr Oak Tool will need to be able to provide to our customers. So there's a lot of exciting things that can be done yet on our digital journey as we use the digital twin and virtual machines. Naresh?
Thank you very much, Eric. Yeah, that was very interesting. When that's the path most of the companies are taking now. When you start with virtual commissioning, or even if you are an OEM supplier or your OEM builder, you need to have a factory twin. So if you have a factory twin, you can actually build or improve your efficiency pretty good. When you can do multiple iterations without having your continuous process improvement team running around all day and out, you can have a twin sitting in your computer and try to change, move around your stations and see how you up your the efficiency without even spending a dime on doing any modifications to your factory or shop floor. But these are some of the basic things, and we are open for questions now. We have 5 more minutes. You can shoot your questions in chat window, or if you want to talk, you can raise your hand in Teams. I will unmute you. If we don't have enough time to answer all your questions today, we will definitely get back to you over emails. So please type in your questions, and we'll see if we can answer everything today.
Okay, Naresh, I see there's a question in the Q&A portion that says,
Okay.
we have a concern about the safety of machine data. Do you have any tech mechanism to protect and address the concern? I'll say a couple words about that, and then maybe you can go on.
Yeah, definitely go ahead.
So I guess let me approach that question from a machine builder process or perspective. A lot of times that's going to come down upon a let's see, a cybersecurity risk assessment. I think we should all be familiar with doing a safety risk assessment. The same needs to happen to when we talk about cybersecurity. Obviously, Burr Oak Tool, as a machine builder, wants to work with our customers to make sure what we provide on our machines is secure and fits into the model of our customer. And then one thing that I think is important to keep in mind as OEMs and machine operators discuss these risks is to consider which data is safe to share with an OEM and which data you don't want to share with an OEM. So the machine itself, there's probably no data coming from that machine and its operation that is necessarily proprietary. It's just the way the machine operates, its performance data. When does a filter need to be changed? Is a bearing getting hot? Those types of things. However, you guys do have, as a machine operator, or a manufacturer, you do have process data that's proprietary to you, and you don't want to let that go. So part of your assessment would then be to identify what data is more of process data versus production data.
Yeah, that's a pretty straightforward answer. Thanks, Eric. We'll go to the next question. So, as experts in special purpose machine. Yeah. All right. So, as experts in special purpose manufacturing machines for the past 50 years, how do you plan to adapt and integrate our digital twin? Yes. So, this is a pretty common question where many people will be thinking about it. Like, you have the tribal knowledge, you know how the machine works, how a third party vendor or a supplier like us or a service provider like us knows how your machine performs. Right. So when we started engagement with Burr Oak Tool, we don't know what the machine they make. But when I said the making digital twin, it's a collaborative effort. So you need to collaborate as a team. So you don't have to tell all the proprietary information that you have, even though we have an NDA in place, but just on the machine philosophy, how it performs, how it has to be done, and also how your machine works together. So these are some of the information we definitely need from you. You train us, you give the knowledge to us, and that's how it is going to be reflected in the digital twin. And digital twin process is also pretty unique. I mean, it's pretty common for all the industry. So only niche thing is going to be just the trickier area is the philosophy of the machine. If you tell us that, that will help us out in commissioning your machine. Do you have any words to add on, Eric?
And again, just from a machine builder perspective, we like to use the digital twin when we're designing a new and innovative product, one that we haven't built before, because there's lots of time during that process to try and condense the amount of time. So as we talked about, doing that software commissioning during the build. Looking to the future, each of our machines is customized depending on the needs. So then when we start talking about a generic machine, well, then we look at how do we modify the model or the virtual or the digital twin so that we can reuse it as much as possible. And think of it as like when we're doing machine retrofits and modifications. I think it's the same process where we use it and continue to let it evolve as our designs evolve. And you keep it current, just like you would your machines.
Perfect. Thank you, Eric. Thank you, gentlemen. We are on time now. I mean, you can always send us an email or ping me a message in LinkedIn. When my name is Naresh Arnagiri, you can connect me over there. I don't know. Eric is in LinkedIn. You're not there, right, Eric? So I'm always there to talk to you more on the technical aspect of digital twin or some other engineering topic I would be interested to talk to. So let us know if you have any questions. Thanks a lot for your time for joining us today. It was really great, and we would look forward to talk to you later. Thank you. Thanks for your time. Thanks, Eric. Thanks for your time. Thanks for joining us.
Thank you, everybody.
Thank you. Thank you, everyone.
Thanks.
Bye.